Welcome to part 3, solving recurrences. So this is part 3 of a series of YouTube videos that I've been doing, trying to explain or trying to understand recursive algorithms. So what we're going to see today is how do we solve recurrences. And in order to do this, I'm just going to do it by example, very, very simple. So remember that in the Towers of Hanoi, well, if you haven't seen my previous videos or you haven't seen Towers of Hanoi, I recommend that you take a look at that, even Google that, so that you know why this recurrence happens in the Towers of Hanoi. But basically, out of a problem of size n, in this case, it was n disks for the Towers of Hanoi, which are right here. We had to solve two subproblems of size n-1 each. So they had less number of towers. Each of the subproblems has less towers. So we had to solve two problems with n-1 disks, and then we have to move one disk at a time. So this is the recursion. This is the recurrence. That is the description of the recursion on the algorithm. So one of the ways that we do it is iterate the sequence. If we iterate the sequence, then we consecutively find the numbers. So first of all, t of 1 is equal to 1, that's the initial condition. Then t of 2 is equals to 2 times t1 plus 1, and we evaluate the actual number is 3, and then we get a 7, and so on and so forth. So we can evaluate the sequence of the first values in the recurrence. So the method of substitution, we're going to see today two methods, method of substitution, and the other one is the recursion trees, the method of recursion trees. And in the substitution method, we make an educated guess. And in this case, well, an educated guess could be the following. Because in the Towers of Hanoi, we are splitting into two problems at each time, then we're doubling up. And so we might compare the numbers that we just got by iterating the recurrence with the powers of 2. If we do that, we realize that t of n has these numbers, 1, 3, 7, 15, 31, and so on. Well, these are the first 5 numbers. And the series of 2 to the n, the powers of 2, are very similar. So we have a conjecture. So this is our conjecture, which is basically the educated guess. We conjecture that Tn in general has the form 2 to the n minus 1. Now we have to prove this because we haven't proved it. We have just shown it for the first 5 numbers, but that's not proof. So to prove this, we use the method of mathematical induction. The base case is the initial condition. It satisfies the equation because the equation that we want to prove is the equation for t of n. And we see that for t of 1, this is exactly satisfied. So the base case is satisfied. The induction hypothesis tells us that we have to assume that for n-1, this formula is correct. So we assume that. And in the inductive step, we basically consider this the definition of the recursion, which comes directly from the recursion. But then we're going to substitute for Tn-1, we're going to substitute the hypothesis. We hypothesize that this is true, so we're going to substitute that in there, and we obtain the following line. And once we develop that by algebra, then we obtain that indeed T of n satisfies 2 to the n minus 1. So if it's true for n minus 1, it's true for n, and that's the basis of mathematical induction. So we can conclude that this is true, and this is a way to solve the recurrence. To remind you about the definition, a recurrence for a function t defined on the integers is an equation that expresses t of n recursively in terms of the previous values of t of k. And to solve the recursion means that we have to find Tn as a function of n not as a function of the previous values of t. So solving by substitution, we have to get an educated guess, which is a conjecture, which can be obtained using iterating the sequence, as I just showed. And then once we have the conjecture, that's not a proof, once we have the conjecture, then we have to prove the result using mathematical induction and the recurrence itself. I've put something in gray for the more advanced viewers. If you know about linear recurrences, they are also called finite difference equations, and usually we solve them via characteristic equations that give us the educated guess. And in that context, the educated guess is also sometimes called an ansatz function. For first order recurrences, we have a theorem that basically uses that same idea, that iterates the first few steps and then proves by induction. And what we have is something similar to a geometric series. So it's of the family of the geometric series. And so we have a theorem that tells us what is the expression of t of n as a function of n, starting with the recurrence. So it's very useful to be able to have theorems like this, because we don't have to do the work all the time. But of course, the assumptions have to be satisfied, and they're not always satisfied. So as an exercise for you, remember the idea of in the second of my videos, I gave you an exercise where I was asking you to write the recurrence for the case of mortgage payments. And so I'm coming back to that example. And if you haven't seen that video, you might want to see it or not. Anyways, so when we have an initial debt amount of A, so this is what's left to pay after you've paid the mortgage, the down payment. And we have an interest rate, which is an annual interest rate of R. And we have monthly payments, which are capital M. So it can be shown that the recurrence in this case is the following: T of n, the amount that you still have to pay at month n, follows this recurrence. It's 1 plus I, where I is the monthly interest, times what you were owing last month, minus the amount M that you have paid that month. So that's the recurrence that that follows. And the exercise for you is to find the solution to the recurrence, and with the solution to show that if the monthly amount is smaller than capital A times I, then it is impossible to pay off the loan. You will owe for it. So as a moral to the story, try to pay your mortgage the sooner the better. All right, so we're going to see now the second methodology, which is recursion trees. And in order to see this, in order to see the ideas, we're going to use again our example number 2, the merge sort algorithm. In the merge sort algorithm, we introduced that by saying I had 8 cards that I wanted to sort. And the idea was to say, look, if I had someone, in that case, I call that person Sam, that could sort packets of 4, then I could easily merge these 2 sorted packages of 4, and I could obtain my full sequence of 8 cards already sorted. And the idea was to recursively use this same method or this same logic. So we're going to see how this leads to a methodology that is called a recursion tree. So for that, I'm going to use my iPad and show you the way that we build this. We start out, so I start out saying, oh, I would like to solve a problem of size n. Because we're going to use this divide and conquer idea, and we're going to divide the size in halves. It is convenient, although it's not mandatory, to assume that n is already a power of 2, so that we can always keep dividing by 2 and obtaining integer numbers as a result. So I'm going to assume that n can be expressed as 2 to the L, and L is an integer. In the example in my video, I was using 8 cards, so that is 2 to the 3. All right, so the idea here was that I was going to hand out sub-problems, and each of them of size n/2, and we had called this person Sam. So this person, Sam, was going to solve problems that were of half the size. Now, once Sam solves these problems, we saw in the last video that to solve the problem at the top level, I need a linear amount of time. So the amount of work that I need to do once Sam gives me the two sorted arrays is C times n. Now, by the same token, Sam was going to call Alex, and Alex was going to provide solving the problem for sizes n/4 each of them. And so let's put this one in green. So once Alex provides Sam with the sorted arrays of size n/4 each, she can do this part of the merging in n/2 operations, order of n/2, and this merging as well will be proportional to n/2. So basically, the amount of work that she's going to have to do herself is C n/2 for this file here on the left, and C n/2 for this file here on the right. And by the same token, Sam was then calling Paul, who was doing smaller problems, dividing the problems all the time by 2, so halving the size. And let's say that this is the last one. Now, at the very bottom, the problem sizes are all 1, 1, 1, 1, 1, 1, 1, and 1. And we have an initial condition that tells us that T1 is equal to 1, let's say. So, well, in this case, it would be equal to C, which is the amount of time the computer gets in order to place that particular value in an array. So what we have here is that once Paul gives Alex the individual ones, like the yellow ones, Alex can perform this particular operation here. When Paul gives him these two, then Alex can perform that operation in an amount of time with a cost that is Cn/4. But he's got 4 problems, 1, 2, 3, and 4. So Cn was Cn/4 plus Cn/4 plus Cn/4. And I guess you can see that in general, in this particular case, so in this particular case, in general, what we have, the observations that we have are the following. At these different levels, we have a work. So we have the notion of work per problem. And we have the notion of number of problems per level. So in this level, the green level, we have a size of problems, which is n/4, and we have 4 of those problems. And so we can calculate what is the total amount of work required at that particular level by adding them up. So this is equal basically to Cn. This is also equal to Cn, and this is also equals to Cn. In this particular case, it turns out that the work per level is as a constant C times N independent of the level. Now let's see, how do we label, how do we number the different levels? And to go from one level of the tree to another one, this is usually called the root of the tree. And the final ones are called the leaves of the tree, the final ones. And the the intermediate steps are called, well, sometimes these are called the children of the previous nodes, or sometimes they're basically called the nodes, the different nodes in the tree. So the two terminologies are acceptable. So how do we label, how do we number the different levels? So it is important to realize that the levels are going to be with half the size at each time. And we're going to have, in this case, 2 problems per size. So it's important to realize that the size of the problem is the one that is important here, because there are as many as needed to end at size 1. So the end one is going to be size 1. So in order to determine how many levels we need, it's important to know the consecutive sizes. And the consecutive sizes in this case are going to be determined by the number that we have. So in this case is half. So level 1, or well, we call the first one level 0. Level 0 is basically n divided by 1. It's just a size n, but that's also n divided by 2 to the 0. Level 1 is n divided by 2 to the 1. Level 2 is n divided by 2 to the 2, and so on. And I guess you can see that in general, level I is n divided by 2 to the I. So how many levels do we need in order to finish at size 1? And for this, we recall that the assumption is that n is a power of 2. So basically what we need here is the last level will be the level such that n divided by 2 to the L is equal to 1. But because n is equal to 2 to the L, then the last level is labeled with the number L. So there's always, this is always going to happen in this particular case. And so the number of levels is L plus 1, because we start at level 0. So we start at level 0, so the total number of levels is L plus 1. So all of that is going to help us to calculate what is the total amount of work required, or the running time, or the cost. The 3 words are used for the analysis of the algorithm. We know here that the work per level was a constant Cn, and there are L plus 1. So basically what we obtain is that the total work, so the final expression for Tn, where n is the highest number, so the total amount of work is basically L plus 1 times Cn. But what is L as a function of n? Well, n over the n is supposed to be equals to 2 to the L, which is equivalent to say that L is log on base 2 of n. So the total amount of work is C times n times log 2n plus 1. And so this way we solve the recurrence for the merging state. In general, it's interesting that when we are using the recursion trees, the methodology. What is important to understand are these salient features. First of all, we need to know how many levels are there. Now, this depends on your recursion. So if we have a recursion that says, for example, Tn equals, let's put here an integer a times t of n divided by b plus another thing, it might be a function of n, then we are dividing here by b all the time. So we will assume that n is of the form b to the power of l. And so we need to determine how many levels are there going to be. If we're dividing all the time by an amount b, in the previous case it was 2, but it could be 3, 4, 5, whatever. So if we're dividing by that, then we need to establish how many levels are there. And in this setup, it will be always L plus 1. For this particular setup, the number of levels will be L plus 1. So we need to decide that, first of all. We need to understand that. Secondly, the interesting thing was how much work is there? So first of all, how many problems or sub-problems are there on each level? Now, that is going to be determined basically by what, this amount A, in case that is an integer. It basically tells you in how many splits do you do each of the nodes. So of course, because this is a tree, each of the nodes is going to have as many children. So the amount A is going to tell you how many children each of the nodes is going to have. And that is going to help you know how many problems are there at each level. So you need to find that out. And the third thing that is very important, of course, is to calculate what is the amount of work. How much work per problem. Once you know how much work there's per problem and how many problems are there at each level, you can calculate the amount of work per level. This is what we did a little while ago in calculating first the amount of work that each of the nodes had to do, and then we added them up here to realize how much work per level we had to do. So in this case, we were calculating simultaneously those things. And once we have all of this, then we can calculate the total work. Because once we have the work per level and the number of levels, we basically just have to add them up. So visually, if you want to see it in the tree, we have to add up the column that we get at the very end. So the recursion trees, we don't always have to draw a tree. Sometimes if there are if the number A here is a very large number, 9 or 12 or something like that, you don't want to be drawing all these little nodes in the tree. It is not necessary. So you can, once you visualize it, you can always work with the table. And so this is what we're going to do now. I'm going to show you the table. So this is the merge sort algorithm that we have. And in general, for the recursion that I just wrote down a little while ago, this will be the recurrence Tn equals A times Tn over B plus Fn. Now this recurrence, the mathematical formula, corresponds to the recursion where a problem of size A requires a number of problems of sizes n over B each, and work per level, which is an amount f of n. So the recursion is related to the recurrence. So the A is the number of children for each of the nodes in the tree. And that's going to give us basically the rate of growth in the tree. That's a very bad number. Well, it's a good number. Numbers are no good or bad. But I mean, if you want to have something that computes very quickly, then you have to be very careful about A, because if A is big, then your computational time is going to grow very, very fast. So A is related to the rate of growth of that tree, roughly. Now B divides the size of problem for all the subproblems. And then F is going to give you the unit cost per problem. And with these elements, we can build a table. So that might be very, that comes very handy. This is an example. In this example, we have the recurrence is Tn is 4 times T of n over 4, and then we add n. So we can see that the number A is 4, number B is also 4, and f of n is the identity. So what I've done here is that I've drawn the recursion tree on the right, because 4 is not such a large number, so it gives them an idea. And then we take a look at the number of problems, number of the number of problems that we have at each of the levels. So in the first level, we have only 1. Well, it's really level number 0 because it's 4 to the 0. So we number the levels starting with 0. And in here, we're going to end up with n subproblems, each one of size 1, which is generally what we do in this type of problems where we always divide by the same number. So this is another example where what I've done is to put a table. And in this table, we can pretty much see that we analyze how much work we need to do. Again, work per problem means the problems are each of the nodes in the trees. And the total work per level is this one. So as before, we identified that the number of levels is L plus 1. In this particular case, we're going to be assuming that n is equal to 4 to the L, because now we are dividing by 4. So in this particular case, we assume that n is a power of 4. And so we arrive at the final level, which is size 1, when we've done curly L plus 1 steps. And in this particular case, the total work is, again, a constant. T of 1 is equal to 1, so it's always a constant. And so that's when we get, again, that T of n is equal to n times 1 plus log base 4 of n. So this is a similar problem to the problem of the towers of Hanoi. The following problem I find a little more interesting. In this problem, A and B are not equal. So in this case, the constant A is 9. This was the one I said, we have 9 subproblems. So each level splits into 9 nodes. That's big growth. And the size of each of the problems is only a third of the parent's size. So it's going to grow quite fast. This is the visual for it. I just did one. I just did one split because my PowerPoint was going to look almost like a spider web. But we can write the table. And when we take a look at the number of problems here, we realize that because the number of problems is multiplying into 9 nodes, whereas the size is only dividing by 3, then at the very end, we don't end up with n problems. When we have each one of size 1, it turns out we have n square numbers. So we have to end doing the, to do the whole computation at the very end, which is at the leaves of the tree, n squared times. And then the work required is basically, like I mentioned before, it will be the sum of this column. So when we sum up this column, we realize that in this column, we have 3 to the I times n work at level I. And so we have to add up all of these numbers. And when we add these numbers, we use the geometric series expansion. And what we obtain at the end is this formula. It's interesting to see now that the growth of this computation, the growth of this algorithm, will be of the order of n squared, which is higher than the 2 previous examples. In the towers of Hanoi, it was n times log base 2 of n. And in the previous example, it was n times log base 4 of n. Whereas now, the amount of work is n squared, which is, but it's still polynomial. So that's the way that we calculate it. Now I'm going to finish this for those viewers that are more interested in the theory of algorithms. There is a theorem as well, as we saw the theorem for the first order linear equations. There is a theorem which is called the master theorem that will give us the rate of growth for recurrences. And in this theorem, it's very interesting to see that we have the same elements as we had previously. A will be as before, the number of children on each of the branches of the tree. So this is going to give us how many sub-problems do we have for each of the problems. So this is the number A as before. And then we have the B is the divisor part. This, remember, that are called in computer science divide and conquer algorithm. So we divide by B, the size of the problems, and we solve smaller problems all the time. So that's the same. And then I'm using the same notation as before. The work per level is f of n. Now, the interesting thing of the master theorem is that the master theorem tells us that the order of growth of the algorithm is going to be of 3 types. Either it's of the order of n log base of A, or it's going to have the n log base of A times log n, or it's just going to be of the order of f of n. And these different rates of growth are going to depend on how fast the work per level will grow. So if the work per level is growing at a rate which is bounded by the n to the log b of a, then the dominant term would be the n to the log b of a. If fn is actually of that order, then we will have the other case. And finally, if f of n is big, oh, sorry, I made a mistake with the formula. So I'm going to have to correct it. Hang on, I will be back with the corrected. This is the corrected slide. I had made a typo in my mathematical formulas, but this is the correct statement of the theorem. I did want to correct that. All right, so this is a way to be able to deal with very complicated algorithms. First of all, so to finalize, first of all, we saw how to use the idea of recursion in order to create algorithms that might be more efficient than trying to do things sequentially. Secondly, we saw that there is a description for those algorithms that use the idea of recursion in terms of mathematical recurrences. And what we saw today was two methods of solution, the substitution method and the recursion tree methods. And I hope you enjoyed it. Thank you very much for listening.